Assalamu alaikum to you all. Uh, in our discussion so far on dynamic programming, we have seen two examples of how to apply DP to solve a problem. In this lecture, we are going to see another example, which will be the final example for dynamic programming. So this is the outline of the lecture. First, we recall how to do matrix multiplication. This, I believe, you must have seen somewhere in one of your math courses. Then we state our problem which we want to solve as the third example. It is called matrix chain multiplication problem. We shall solve it using the same 4 steps of solving DP problems that we already outlined in the previous lecture. These are namely: characterize the structure of an optimal solution, recursively define an optimal solution, and then apply DP technique to compute the optimal solution. As you recall, there are 2 ways of doing it, either using the bottom-up approach or using memoization. So initially we will solve the problem using the bottom-up approach. And then we look at how to construct the optimal solution. In other words, what are the routes to follow to actually obtain the optimal solution that we got in step 3. Then we look at the other option for solving the problem, which is using memoization. And we conclude the example by looking at a summary of how to solve this particular problem. Then finally we take a summary again of dynamic programming problem solving approach by stating the main elements that are involved. And this will be the end of the discussion on dynamic programming. So let us start with the first topic, which is recalling how to do matrix multiplication. You will recall that if you have 2 matrices, let us say A and B, where A is of dimension P by Q, where P is the number of rows and Q is the number of columns, and another matrix B of dimension Q by R, where Q is the number of rows and R is the number of columns. Then you can multiply these 2 matrices A and B to obtain another matrix C. However, there is a condition for you to be able to do that, as you may recall. For you to be able to multiply A and B, then the number of columns of A must match the number of rows of B. Okay, so here the number of columns Q of A must match Q, the number of rows of B. Okay, if these conditions are met, then you can multiply the 2 matrices to obtain another matrix C, which is defined by this formula. So basically, as you may recall, each element of the resulting matrix C, each element ij, is computed by multiplying the elements in row I of matrix A times the elements in column J, okay, of matrix B, and taking the sum of the products. Yeah, this is how you can obtain the resulting matrix, by computing each element using this formula one by one. This algorithm actually shows how two matrices can be applied. Matrix multiply. So it receives two matrices, A and B. And the first thing it does is it checks whether these two matrices can be multiplied. So here it says if the columns of A is not equal to the rows of B, then stop immediately and return an error, because the two matrices then cannot be multiplied. But if they can, then define a new matrix C of dimension A dot rows times B dot columns. Yes, the resulting matrix will have rows equal to the rows of A, but columns equal to the columns of B. Okay, now how do we populate this matrix C? We need triple nested loops. First, we vary I across the rows of A. So go across the rows of A for I from 1 to the total number of rows in A. Then for each row, vary another variable J across the columns of B. Okay, so now for each pair of these variables I and J, we compute a value Cij corresponding to element Ij in our resulting matrix. Now how we do it is by going through the columns, the elements in the row I of A, basically the columns, against the elements in column J of matrix B, taking the products AIK, BKJ. Okay, this is for K from 1 to the number of columns of A. Or if you like, the number of rows in B, because Q is the same actually for the number of columns of A or the number of rows of B. Okay, so you will be computing this Cij and keep updating. By the end of this loop, we will have obtained a value for Cij. And then you go back to the outer loop and look for the next Cij. So this algorithm will eventually compute the elements of the resulting matrix C. To make this more clearer, let's take a concrete example. So suppose you have these two matrices, A, which is of dimension 3 by 3, and B, which is of dimension 3 by 2. So here, as you can see, these two matrices are compatible because the number of columns of A matches the number of rows of B. So how do we compute the elements of the resulting matrix C? As we said, to compute each element Ci, we go through row I of matrix A and column J of matrix B, multiply the elements and take the sum. So here, for example, to get 1 or 2, we will say 1 times 1 plus 8 times 7 plus 9 times 5. If you add all of this, it will give you 1 or 2. And that is our element number 1, 1 of the resulting matrix C. To get element number 1, 2, you take row 1 against column 2 of B. So row 1 of matrix A, column 2 of matrix B. Take the sum of the products and you get the element. To get this one, you multiply row 2 against column 1 to get 2, 1. Okay, row 2, column 2 will give you this element, and so on. So this is how you multiply matrices. We observe that there are going to be P times R total entries in our resulting matrix C, where P is the number of rows of A, so in this case 3, times R, where R is the number of columns of B. So 3 times 2 is 6. This is the total number of elements in C. Now each one of these PR elements is going to cost Q operations in terms of the number of multiplications needed to obtain it. Because as we know, we have to do 1 times 1, which is 1 multiplication, 8 times 7, second multiplication, and 9 times 5, which is third multiplication. So there are 3 multiplications needed to compute each of these elements. And that 3 correspond to the Q. Q being the number of columns in A or the number of rows in B. So we can say that therefore to compute this matrix C, the total cost in terms of number of scalar multiplication needed is going to be PQR. Okay, so for these 2 matrices to be multiplied to obtain C, we have to do a total of P, which is 3, times Q, which is 3, times 2, number of multiplication. So 3 times 3, which is 9, times 2, which is 18. There are going to be 18 scalar multiplication needed in order to compute C. So that is basically the cost of computing this matrix C, PQR. Okay. Now we should also recall, as I already mentioned, that we can multiply 2 matrices A and B only if they are compatible. And 2 matrices are said to be compatible if the columns of A is equal to the rows of B. Now it is possible that AB is defined, that is multiplying A times B can be done, but multiplying B times A cannot be done because of B times A being not compatible. Okay, that is the number of columns of B doesn't match the number of rows of A. It is also possible that they match, so you can do both A and B, or you can do both AB and BA, but you will find the result is not equal. Okay, so even if you can do both A times B and B times A, it is possible that the result may not be the same. Now, because of these 2 issues, we conclude that matrix multiplication is not commutative. I'm sure you know the term commutative. It means AB equal to BA. So if in this case it is not going to be possible, then we say the matrix multiplication is not commutative. Okay, so this is an observation. Okay, now we said our problem is going to be about matrix chain multiplication. So what does that mean, chain multiplication? Now if you have a sequence of matrices A1, A2, A3 and so on until AN, then chain multiplication simply means multiplying these matrices all together to obtain one matrix. Okay, so A1 times A2 times A3 times A4 and so on until AN is what is called matrix chain multiplication. Obviously, you have to be multiplying 2 matrices at a time. So for example, you could decide to multiply AN times, or rather AN minus 1 times AN. So that will give you one matrix. Now multiply AN minus 2 with that result. It will give you another matrix, and so on. So you keep doing that step by step until you end up with one single matrix. This is called matrix chain multiplication. Now, the good news is that matrix chain multiplication is actually associative, or matrix multiplication is associative. Okay, even though it's not commutative, it is actually associative. What does that mean? It means if you have three matrices to multiply, for example, then it doesn't matter which two of them you do first. You can do A1 times A2 first to get a matrix and then multiply the result with A3. Or you could do it the other way around, multiply A2 times A3 to get a result and then multiply A1 times that result to get the overall result. Okay, so it doesn't matter where you put the parentheses. Okay, therefore we say that parenthesization of a matrix chain multiplication does not change the result that you're going to obtain. Okay, so this is very important information. However, while the order of parenthesization does not change the result, it can significantly affect the efficiency of the overall multiplication operation. Let's take an example to illustrate this point. Suppose you have three matrices, A1 of dimension 10 by 100, so 10 rows, 100 columns. A2 of dimension 100 by 5. And A3 of dimension 5 by 50. Okay, now suppose you opted to multiply A1 by A2 first before you multiply the result with A3. The question is, how many multiplications are going to be involved? Well, as we just said in the first slide, multiplying A1 times A2 will give you PQR, or will require PQR number of scalar multiplication, where P is the rows of A1, Q is the columns of A1 or the rows of A2, and R is the columns of A2. So in this case, for example, the cost of A1 times A2 will be 10 times 100 times 5. Okay, rows of A times columns of A or rows of A2. Okay, rows of A1 I should say, times columns of A1, which is the same as the rows of A2, times our R, which is the columns of A2. If you multiply this, you will have 5,000. So there's going to be 5,000 scalar multiplication to compute A1 times A2. And of course, the matrix that you're going to get will be of dimension 10 by 5. Okay. So now we need to multiply our result, which has this dimension, times A3. So what is the cost of that? Multiplying the result with A3 again will involve PQR number of multiplication, where P is the rows of our resulting matrix from the previous operation, Q is the number of columns, and R is the number of columns of A3, which is 50. So 10 times 5 times 50. Okay, if you do this, you're going to get 2,500 multiplication required. Therefore, overall, to multiply these three matrices following this parenthesization will require 5,000 plus 2,500 scalar multiplication, which is 7,500. Okay, now let us look at the other way around. Suppose you decided to do A2 times A3 first before you multiply A1 with the result. Okay, so what is the cost of A2 times A3? It's going to be 100 times 5 times 50. Okay, 100 times 5 times 50, PQR. If you multiply this out, it's going to be 25,000 already, 25,000 scalar multiplication. And you will have the result, a matrix of dimension 100 by 50. Okay, now we need to multiply A1 with this result. So A1 times the result will cost you 10 times 100 times column of the resulting matrix, which is 50. So 10 times 100 times 50 is, will you believe it, 50,000 scalar multiplication. So the overall number of scalar multiplication required, if you follow this approach, is 75,000 scalar multiplication. Wow. Comparing this with the previous results, this is 10 times more costly than if you follow this parenthesization. Okay, so the point is, say one order of magnitude difference. Okay, so basically the point is, even though matrix chain multiplication is associative, it is still important to know which approach will give you the least expensive, because although you will get the same matrix result, the number of operations involved can differ significantly, as we can see here, one order of magnitude difference. Now this is the motivation for our next DP example. How do we actually find out which parenthesization will give us the least cost? Okay, let us take the problem. So our problem for the matrix chain multiplication is this. Given dimensions P0, P1, P2, and so on until Pn, corresponding to matrix sequence A1, A2, and so on until An, where matrix AI has dimension Pi minus 1 times Pi. So for example, matrix A1 will have dimension P0 times P1. Okay, A2 will have dimension P1 times P2. A3 will have dimension P2 times P3, and so on. So assuming you are given this dimension, okay, it's only this you need for this problem. You don't need the matrices, because we're not trying to actually multiply the matrices. We are only trying to know how can we do the multiplication. How do we parenthesize the operation? Okay, so given this dimension, determine the multiplication sequence that minimizes the number of scalar multiplications involved in computing A1 times A2 and so on until An. That is, determine how best to parenthesize the multiplication in order to minimize the cost involved. And the cost involved here is the total number of scalar multiplication. How can we minimize it? So this is the problem. Again, we emphasize the objective is not to find the product of the matrices or of the matrix chain, but simply to fully parenthesize the sequence in such a way that the multiplication, if it needs to be done, will be efficient. Okay, obviously finding all possible ways to solve the problem and then choosing the best one is going to be very expensive. That is, the brute force approach is going to be exponential. To look to see how Just consider a chain of size 4, and you see the number of possibilities involved. Okay, to multiply these matrices, we can have this way, or this way, or this way, or this way, or this way. So just for 4, we have these possible options. This number will multiply as n increase, or as n increases, or as the size of the chain increases. Therefore, this problem is going to be, the brute force approach is going to be impossible to solve actually. Instead, we're going to try and solve this problem using dynamic programming. And that means following all the 4 steps that we outlined in previous lecture in solving DP problems. Okay. So the first step is characterizing the structure of an optimal solution. This is the first step. We have to find how to characterize the structure of an optimal solution. Let's see how this goes for this particular problem. Let us first start by adopting a notation for convenience. Instead of saying AI times AI plus 1 and so on until aij, we're going to simply denote it as AI to j. Okay, so a simple notation for convenience. Now suppose that an optimal parenthesization of AI to j splits the product at an index k. Okay, so that we have the first part from AI until AK, and the second part from AK plus 1 until AJ. Suppose that this splitting is optimal. Okay, we don't know the value of K, of course, yet, but we're going to make an assumption. Suppose that an optimal parenthesization of the product can be obtained by splitting the sequence at an index K, where K is between I and J. So less than or equal to I, but strictly greater or equal to I, but strictly less than J. Okay, so suppose this gives us an optimal solution. Okay, then we can say that AI to AJ, the optimal solution for AI to J, can be written as the product AI to K times the product AK plus 1 to J. Okay. So now if this is optimal, okay, if this splitting will give us an optimal solution, then the parenthesization of the prefix, meaning the left hand side, must also be an optimal parenthesization. And similarly, the postfix, or the right hand side, will also be an optimal parenthesization for that particular subproblem. Okay, let us try to prove this using what is called copy and paste technique. So to prove that if this is optimal, then each of this is optimal as well, let us assume, for assumption's sake, that there is a less costly way of parenthesizing AI to K. Suppose there is a less costly. Now, if you substitute that option in our original equation here, it means you're going to get a smaller cost, a smaller overall cost of multiplying AI to j. But this will be a contradiction, since this we say is the optimal solution already. Okay, yeah, let's read the statement again. If there were a less costly way of parenthesizing AI to k, we could substitute that one in the parenthesization of AI to j and produce a parenthesization with a lower cost than the optimum. Okay, and this obviously is a contradiction. Therefore, the conclusion is that the parenthesization AI to k is optimal for that subproblem, and also the parenthesization of ak plus 1 to j is also optimal for that subproblem. In other words, an optimal solution to an instance of a matrix chain multiplication contains within it optimal solution to subproblems. In other words, this our characterization of the structure of the matrix chain multiplication exhibit what is called optimal substructure property. And basically, this is the characterization we need as a first step in solving the DP problem. Characterize the solution in a form that exhibits optimal substructure. And we have seen that in this way it will exhibit optimal substructure property, where the optimal solution has within it solutions that are optimal to subproblems. Okay. Next step is to try to come up with a recursive optimal solution based on our characterization in the first step. Okay, we need to find the cost of an optimal solution recursively in terms of solution to subproblems. For this, we need another notation. Okay, to determine the minimum cost of parenthesizing our sequence AI to j, let us define a term mij to mean the minimum number of scalar multiplication needed to compute the product AI to j. Okay, so this is the minimum number of scalar multiplication needed to compute this AI to j. Okay. Obviously, if I is 1 and j is n, then you are multiplying the whole sequence from 1 to n. And that means this is the overall optimal solution that we are looking for. Okay, the optimal solution of multiplying the sequence from 1 to n. Okay. Okay. Now, what will happen if I is equal to j based on our definition here? If I is equal to j, then we are trying to find, according to this definition, the number of scalar multiplication needed to multiply matrix AI to I, which basically means just a single matrix. And of course, in this case, no scalar multiplication is needed, and therefore mi to I is 0. This is true for all I from 1 to n. Okay, so if it is just one matrix, basically what we are saying is the cost is 0 because there are no scalar multiplication involved. Okay, so this will give us our base case in terms of trying to define our recursive definition. Okay, based on this definition, mii is always going to be 0. Now let us try to find the recursive part of the definition. Okay, so consider the problem of parenthesizing a sequence AI to j. Okay, where I and j can vary from 1 to n. Okay, Again, as we assume, suppose that we can split this sequence at an optimal index k, or at an index k that will give us optimal solution. Then we can represent this ai to j as ai to k times a k plus 1 to j. Okay. Yeah. So assume that the optimal parameterization split the product at k with optimal value. Then we can represent our recursive definition for mij as mik, because obviously this will cost mik, plus mk plus 1j, because again the right hand side will cost, according to our definition of mk plus 1 comma j. However, after obtaining the two matrices from these two subproblems, we still need to multiply them to get the overall solution. So in addition to the minimum number of multiplication needed to get this part, plus that needed to get this part, we need the number of multiplication needed to obtain the result of applying the two matrices. Okay, and that, according to what we already saw, will be PQR, where in this case P is simply the number of rows of A, so it's going to be PI minus 1, okay, times PK, okay, the number of columns of where we do the splitting, and PJ, okay, the number of columns of AJ. Okay, so this is the cost of multiplying the two sub results here. So the overall result of the minimum number of scalar multiplication needed to multiply ai to j will be given by this formula. Okay, so first this is mik, and this is mk plus 1j, and now we need to multiply them together to get the overall result, and that will cost pi minus 1 times pk times pj. So this basically gives us our recursive definition. But there is an issue here. We don't know what the value of k is. We just assume. We say suppose k is somewhere where if we assume it, we will have an optimal solution. But to actually know the real cost, we have to check for all possible values of k. Therefore, our recursive definition can be stated as follows. So mij is going to be 0 if I is equal to j, or is going to be given by this formula if I is less than j. Okay, so we're going to look at all possible values of k, for k varying from I until just less than j, until j minus 1. Okay, those are the possible values that k can take. Okay, there are j minus 1 possible values for k, and they are I plus 1, I plus 2, and so on until j minus 1. So if we want to know the exact optimal solution, we have to check all the possibilities, and that means taking the minimum over all the possible values of k from I until j minus 1. Okay, this is basically the recursive definition that we need. If we wish, we can go directly and implement this as a recursive method, and it will give us the solution. but obviously it's going to be very expensive because this is going to be making a lot of repetition. We are basically doing brute force here because we have to take the minimum of all possibilities for each I and j. Now we're not going to do that. Instead, we are going to try and see how we can apply DP, dynamic programming, to solve this seemingly expensive recursive definition. So having obtained a recursive formulation for the optimal solution, the next step is to compute the optimal cost. Obviously, we can go ahead and implement this formulation using a recursive method, but doing so will be very expensive. Okay, computing the optimal solution recursively will take an exponential time because, as we saw in previous example, since this is going to check all possible cases and there will be many repetitions, the problem is going to be exponential. So instead of doing that, we're going to try and see if we can avoid repetitions by employing DP technique. Now, to do that, the first step usually is to see if you can identify the number of subproblems involved. Okay, how many subproblems are we going to have in this matrix chain multiplication? As we can see for Mij, basically we are varying the I from 1 to n and also the j from 1 to n. So if you think about it, this is like a two-dimensional problem. We are varying both I and varying j. So in terms of the number of subproblems involved, it's actually going to be theta of n squared. Okay, as you can see in this table, I will vary from 1 to n and j will vary also from 1 to n. Okay, so overall, therefore, the subproblems you're going to have is going to amount to theta of n squared, or let's say big O of n squared. Okay, yeah, because the parameterization of ai to j is going to involve varying I and j between 1 to n. So effectively, this is what you have. However, you will not, so here is saying one problem for each choice of I and j. So that will give you the number of subproblems you have. However, as you can notice in this table, we're not going to need actually all the n square subproblems, because there's a condition here, I must be less than or equal to j. So I cannot be greater than j. Therefore, the bottom half of this table is not going to be needed. For example, here when I is 2 and j is 1 is not allowed. I cannot be greater than j. And the same thing for the rest of the squares in the bottom here. So actually, these are our subproblem. These are the number of subproblem involved. Okay, this is the first step in trying to see if you can employ DP to minimize the number of computations involved. Identify the number of subproblem involved. So these are the number of subproblem. The next step is to try and see if you can order the subproblems so that the smaller ones are solved first and saved in a table, so that when you need them again, you just recall them from the table. This is what we are going to try and do in the next slide. Okay, so this is our recursive solution. So again, the question is, how do we fill the table we saw in the last slide in a bottom-up manner? so that we utilize previous results. Okay. Now, as we can see from this equation, the cost Mij, which is the cost of computing the matrix chain products of all the matrices, and there are j minus I plus 1 of them. Okay. It depends only on the cost of computing the matrix chain products of fewer matrices. In other words, the number of matrices involved here is much more than the number of matrices involved here and the number of matrices involved here. Okay, because this goes only from I to K. Okay, and this goes only from K1 to J, whereas this one goes from I to J. Okay, that is to say, for K from 1 to J minus 1, the matrix A to K is a product of fewer matrices, which are K minus I plus 1, usually the upper limit minus the lower limit plus 1. These are the number of matrices involved. It's going to be less than the number of matrices involved in solving the original problem, which are J minus I plus 1. And similarly, the matrix chain A to K plus 1 to J will contain fewer matrices, and they are simply J minus K, because this time J minus K plus 1, minus 1 plus 1 will cancel out, so you just have J minus K. So the number of matrices involved in this product are also going to be less than the number of matrices involved in the original problem. So this is an interesting observation, okay, because it means if we can fill that table such that we start with those matrix chains that are smaller, then we will find that by the time we come to compute matrix chains that are of larger length, we will have already solved the optimal solution to their subproblems. Okay, so this is the conclusion. It says, thus the algorithm should fill the table M in a manner that corresponds to solving the parameterization problem on matrix chain of increasing length. Okay, so start with those of length 1, for example, which are trivial. If the matrix is just 1, there is nothing to do, it's no multiplication involved, so they are all zeros. Then you go to those of length 2. Okay, if we have only 2 matrices to multiply, then 3 matrices to multiply, then 4 matrices to multiply, and so on, until you reach the maximum involved from 1 to n. So this is the strategy, as we're going to try and explain again in this table. It says start with length 1. Well, for length 1, I is equal to j. Okay, so basically we are talking about this diagonal. See here, 1 1, 2 2, 3 3, 4 4, 5 5. So we are saying solve the subproblems first. Solve the subproblems of length 1. And as we know, solving these problems is trivial. They are all zeros because no multiplication actually is involved. They are just single matrices. Okay, now once you do that, then you should consider those matrices of length 2. Okay, so for those matrices of length 2, the relationship between I and j is that j is I plus 1. So basically, for example, if I is 1, then j is going to be 2. So we are talking about from 1 to 2. Now, from 1 to 2, k can have 2 possible values. K can be the I itself, which is 1, or well, actually only one possible value because it cannot be j. So k will have only one possible value. Okay. Now, if you look at our table, the subproblems that satisfy this property, they are actually in this list, just above the diagonal. Okay, as you can see here. See, for example, here, when I is 1, j is 2. Okay, j is 1 plus 1, so 2. Similarly, when I is 2, j is going to be 3. Okay, so again, we are saying after you solve those subproblems of length 0, then solve the problems of length 1. Then solve the problems of length 2, and so on. So in other words, solve the subproblems in increasing order of length. Length being the number of matrices involved in the chain. Chain 1, chain 2, chain 3, and so on. Okay, so you see that you are actually going up this table in this manner. The last one is actually the real problem we want to solve. We want to solve the problem of chain from 1 to n. Okay, so you see, by the time we come to solve this, we will have solved all the previous subproblems because we are solving them diagonally like this. This is the idea. Yeah, so the M1n is actually the optimal solution that we are looking for. Okay, so we shall compute rows from bottom to top and from left to right. So row 1, then row 2, and row 3. So top to bottom, left to right, as shown by these arrows. This is how we're going to solve these subproblems. If we do that, we will see that we will not be repeating computing the subproblems. By the time we come to solve them, to solve the bigger problem, the subproblem needed by that bigger problem are already solved. This is the idea. And as I emphasized, the bottom half of the table is not required because for those cells, I is greater than k. Now to see this problem more clearer, let us try to compute or identify the subproblem needed to solve the problem M25. Okay, M25, according to our recursive definition, I is 2, M is 5. So J is going to vary from 2 to 4. So K is going to be varying from 2 to 4. So for the first value of K, which is 2, this is what we're going to have. So MIK, where K is 2, plus MK plus 1. So K plus 1 is going to be 3, and J will be 5, plus the result of multiplying the resulting matrices, and this is going to be Pi minus 1. So I is 2, therefore I minus 1 is 1. Then Pk, okay, K is 2, and then Pj, well, J is 5. Okay, so this is one choice where K is 2. K can also be 3. So if K is 3, this is what you will have according to our formula: M2K, MIK plus MK plus 1J. So in this case 4, 5, plus again the P1 and the P5 are going to be constant for this particular problem. It is the PKs that will vary depending on your choice of K. Okay, and the last possible value of K is 4. Okay, remember K cannot be J. It can only be from I until J minus 1. So 2, 3, and 4. Okay, So if k is 4, this is what you have according to our formula. Now these are the equations you must solve, and then choose the minimum among them. The question is, if you look at our table, what are the sub-problems needed to compute 25, to compute M25? Okay, so as you can see from these three equations, to compute the first one, we need 2, 2. Okay, 2, 2 is the one here in blue, plus 3, 5. So problem 3, 5 is here. Okay, both of them, looking at it diagonally, are below this diagonal. So by the time we come to solve this, they will have been solved. Similarly, if you take the next option for k equal to 3, it will involve subproblem M23. Okay, 2, 3 is here, which is right, plus M45. Well, M45 is here. Okay, plus a scalar multiplication of these dimensions. So again, you will see that by the time we come here, these are already solved. Okay, and finally, for the last option where k is going to be equal to 4, we will have M24. M24 is here, I is 2, j is 4, so it's here in green, and M55. Okay, I is 5, j is 5. This is M55. Okay, plus the scalar product. Okay, so what this illustrates is that if we really solve the problems in bottom-up manner, as we said, we will see that by the time we come to solve a problem, all its sub-problems will have been solved. So we just need to read them up from our table. And actually, this diagram is also showing us how the sub-problems are related to the real problem. Okay, they are just the problems needed to, if you like, intersect between this row and this column. The cell at which we are looking for the problem, just go to the right and to the down, you will obtain the sub-problem needed. Okay, so for example, to solve the overall problem 1,6, we only need this and this. Okay, so going across the row and across the column, the intersection will give us the solution for the overall problem. Okay, now to make it easy to see, we shall rotate our table 45-degree clockwise, so that you can really see we are solving the problem in a bottom-up fashion. Okay, so solve those of length 1, they are in this bottom row, then those of length 2, then those of length 3, and so on, in that way. Okay, now so the values of Mij depend only on the values previously computed. Yeah, this is the conclusion here.